So, hello everyone. My name is TSUYOSHI Murata from Tokyo Institute of Technology. Thank you for inviting me. I'm happy to be here. Because 3 years ago I was invited as a speaker of Marami 2016, but my mother was hospitalized and she was in a very serious condition. So I had to cancel everything and cancel the talk at Marami. So I, I'm very sorry for the organizers 3 years ago, and I'm very happy to be here. My mother is still okay right now. Okay. And one thing I should mention is that the slides, the main slides today will be available at the website, www.net.c.titech and CJP. So if you would like to see the slides, please check the website later. Okay, so today's talk is about some kind of combination of deep learning and the complex networks. So I'm sure that this conference is the researchers of complex networks. So everyone here loves the networks, and many of us do the community detection and invent efficient algorithms and visualize the network and model the network. So there are so many tasks in the field of complex networks, and I'm also one of the researchers in this field. But at the same time, as you all know, the deep learning is very popular in the field of AI and the machine learning. So the deep learning is composed of the many layers of neural networks, and it is very it shows very good performance in the field of image recognition and the voice recognition and the natural language processing. So this is the boom in the field of AI. So what we are some of the researchers of complex network are trying to do is to how we can combine the research of complex network and the deep learning. So I think there are two approaches. One is to regard the neural networks as a complex network. As you know, the neural network itself is a network. So one famous approach is the decompression. And it is a kind of attempt for downsizing the size of the deep neural network so that it can fit to the memory of the limited the devices of the limited memory, such as mobile phone or some other devices. So the input is a big neural network, and the procedure is to prune unimportant edges and introducing quantization. So the small difference of the weights are regarded as the same. So in order to save some memory, and do some introduce Huffman coding in order to save the size of the neural network. So that is one way for doing network analysis in the field of neural network. That's one approach. But in this talk, we will try to focus on another aspect of the combination of the complex network and the deep learning. So it is to utilize the neural network for the task of complex network. And I think there are two main approaches. One is the network embedding, and the other is a graph neural network. I will talk one by one. So the outline of this talk today is to talk about the network embedding, and we will introduce some of our research activities regarding the network embedding. And the second topic is a graph neural network. And this is, we are now doing some research on this topic also. So some of the research appears in conferences, and this result will be presented in the Complex Network 2019 next month in Lisbon. So, I hope many of you will attend the conference next month. So the network embedding or representation learning is to transform the network structure into vectors, and then that vectors are used for the some tasks such as clustering and classification and link prediction. So as I said previously, this room is the researchers of the networks, so we love networks. But the network embedding crashes the network structures into vector representation. So I personally don't like this idea, but this approach is very popular in the field of machine learning because the performance of the classification and the link prediction is much more better than the previous state-of-the-art methods. So this is very popular. And this picture is borrowed from the website, the Awesome Network Embedding. So in order to make a good network embedding, we have to think of some points. So it is a kind of transformation of the network structure into the vector space. So the two nodes that are close to each other in the original network should be located closer in the vector space. So the word, closer or similar is very controversial. So we have to think, what is similar in the graph? And we need to learn the encoder. That is a function for mapping from the original network to the vector space. So, and there are several approaches, adjacent-based or multi-hop-based and the random walk-based approaches. So the similarity on a graph structure is not easy to define. So there are so many challenges of the network embedding. So in general, the graph has a very complex topological structure. So the methods for the image recognition cannot be directly used in the field of networks because in the field of images, the pixels are located in regularly. But in the case of network nodes in a very far apart can be connected. So it is no spatial locality like grids, and the methods for images do not work in the field of network. So that is one point, one challenge is. And another challenge is defining similarity in network is not always easy. So because some nodes have attributes. So we have to think of the combination of the attributes and the structures of the network. And as you know, there are several types of networks, such as sign network, directed network, and multi-layer network, and a temporal network. And many researchers of machine learning are inventing some methods for the each types of the network embedding. So the sign network, directed network, and so on. And these are the very hot topic right now. And so how we can combine these embedding methods is another challenge. So there should be a sign directed network and so on. And there are so many papers and survey on the link, network embedding paper is here, and this is the tutorial of WWW18 last year. And the Awesome Network Embedding is contains many papers and links, papers and codes regarding the network embedding. The awesome, something is a very good keyword for searching for the web pages. So the awesome network analysis or awesome deep learning. So you can find the resources regarding that topic. So yeah, I would like to explain some of our attempts regarding the network embedding. Yeah, one is the paper that appears in ICDM last year, and yeah, another one is the attempts for the embedding of the multi-layer networks that appeared in a workshop collocated in a World Wide Web conference. So the first one is the learning community structure with variational autoencoder. So this is the work done by the PhD student in our lab. And it is a kind of extension of the variational autoencoder. It is a kind of generating models for the classification and for generating similar entities. So this is knowledge, the techniques in the field of images. And the variational graph autoencoder is an extension of this method to graph structures. So, and his work is doing another extension, for the VGAE. And he introduced, multiple Gaussian distributions for this VGAE in order to, make a correspondence to the nodes in the communities to the each of the distribution of the Gaussian. So that is that is a very brief outline of his talk, and I will show some slides regarding the his paper. But I don't have enough time to explain the detail. So if you're interested in, you can check the paper. So this is the outline of the his research. The modeling the network is very important, and when we introduce when we make a network model, so we observe the network and show some properties and develop some models, and that models can be used for making a similar network structures. So it is a handcrafted one. So and another topic is community structure. So I don't have to talk about the details of the community structure here. And in order to model the community structures, there are approaches for the generative model, and the generative model is popular in the field of images, so that the similar images, face images or handwritten images can be generated based on a generative model. And in the field of the this is a slide of the stochastic block modeling. So that is a kind of the modeling of the network. So based on the graph data, we make an inference of the parameters of the model, and that learned model can be used for the generation of the similar network. So based on the stochastic block modeling, we can model the network having a community structures and rather disassociative structure and so on. So this is a stochastic block model is a very popular, and there are several advantages of the stochastic block modeling, but there's other disadvantages, such as requires prior knowledge and community structure, and is too general. So we introduce some kind of the knowledge of the deep learning. So this is the same picture that I explained, the network embedding. So variational variational autoencoder is to introduce some distribution in between the network and the vector representation. So adding a sampling distribution, so we can make the generative model more generalized. And so this is the very popular method in the field of images. So introduce a Gaussian distribution between the in the middle. So the pictures is encoded in a Gaussian distribution, and that Gaussian distribution is used for decoding the original figures. So the variation of graph autoencoder is very similar. The graph structure is encoded in a Gaussian distribution, and that distribution is used for the decoding. So this is the this part, the graph convolutional network is used. So the detail can be skipped. So there's some weaknesses of the variation of graph autoencoder. So there are some the prior knowledge some kind of effect, center pushing effect appears, and it still requires two-step approach for finding communities. So that is a weakness. So introducing a multiple distribution here can make a solution for these situations. So that is the answer. So I know that the time is very short in order to introduce this work in a detail. So that is the essence. And so our proposal is the variation of graph autoencoder for community detection. So this is the schematic figure, and there's some mathematics of the loss function, and we did some experiment using a well-known data set. As you might know, the data set for the this type of research is very small compared with the other researches in the field of complex network. But the graph neural network, the experiment with the graph neural network is very computationally demanding. So so it is rather normal to use this type of rather small-scale network for the experiment. So we did some comparison with the other methods, and show the results, and the performance is better than the other methods. So that is the essence of this research. So I will go back to my talk, and this is his slide. And another research is to embed a multi-layer network. So he's a student in a lab, and in order to do a good embedding of the multi-layer network, we have to think about the similarities between layers, and introduce layer vectors that shows the similarities among the layers. And of course, each node in each layer is embedded in one space, and the embedding of each node in each layer is computed as a combination of the layer vectors and the embedding vectors, so that the better embedding can be obtained. So this is another work. So so this is the embedding, and there's several types of the networks. So that's why we have to think of a multiplex network. So and in order to make a good embedding, we have to think of the relations among each layers. So, and the task is the link prediction in multiplex network problem. So yeah, the quality of the embedding can be tested with this link prediction tasks. And yeah, so we have to think of how we can combine the information of the other layers for the embedding. So the similar layers should be considered at the same time, and some knowledge, knowledge should be augmented in order to get a better embedding. And there are several embedding methods for the single layer network and the multiplex network, and some other network based on tensor decomposition, tensor factorization. And as I said previously, this research introduces layer vectors in order to show the similarities of the layers. And embedding vectors are combined in order to find the final embedding. So the our method enforces the vector for the same node in the layers to be close to each other. So that is enforcing. So if we independently embed each layer, so the location should be quite different. So we make some kind of enforcing so that the position of the the corresponding nodes should be similar to each other, close to each other. And we introduce a layer vector in order to show the similarities of the layers. And I will skip the mathematics, and the experiment is done by the rather popular multiplex network, and the performance of the link prediction is good. So this is another example of the regarding the network embedding. And for the second part of this talk, I will talk briefly about the graph neural network. So how many? 10, 20 minutes? Okay, so I will explain about this. And what is graph neural network? That is the generalization of the neural network model for graphs. And basically the neural network is for the vectors or the images, not for the graph structures. So we but there are so many network data, so it is worth trying to extend the neural network into the graph structures. So, but it is not so simple, because graph structures are irregular, and it is quite different from the grid structures. And there are two approaches for the convolution. Convolution is a very main part of the computation of the neural network. So the spectral-based convolution is rather mathematically clear methods. And it removes the noise from the graph signals. So it is based on the graph signal processing methods. So it is very good in the field of in a mathematical point of view, but it cannot be applied to the several types of the network, and the computation of the identity composition of graph Laplacian is very time consuming. So these days the spatial-based convolution is rather popular in the field of machine learning. So it aggregates features from neighbors, and it allows the edge features. So it is rather flexible, and it can be computed in a faster way if we wish. So the second approach is rather popular in the field of machine learning these days. And there are several applications of the graph neural network. One is the computer vision and the recommender systems, and the traffic forecasting of the traffic speed, and chemistry, because the molecular structures are represented as graphs if we regard the atoms as nodes and bonds as edges. So the graph neural network is very eagerly studied in the field of chemistry and bioinformatics. And we have to say why the graph neural network, graph convolutional network is hard to train compared with the cases of images. So this is the picture appeared in the paper appeared in AAAI 2018. So if we introduce too many layers for the convolution of the graphs, so almost all the nodes are converged to the same values. So introducing too many layers is good for the accurate recognition of images. But in the case of graphs, it is not good because all the nodes will converge to the same value. So it doesn't work at all. So, and there are several survey papers published last year and this year, and the paper is on archives. And there are so many, the list of the must-read papers, the 9 survey papers and the 44 papers for models, and more than 100 papers for applications. So it is a very hot topic, and there's so many publications, and the resources are available in the website. And this is the research appeared in the KDD this year. So this research tries to introduce a deeper graph convolution network. So in this research, the neighborhood expansion is restricted within the clusters. So the in order to avoid the situation that all vertices will converge to the same value. So this is an attempt for the deeper graph convolution network. And there are some researches of the power of the graph neural network. So how powerful are graph neural networks? So, and the author of this paper says that the graph neural networks are at most powerful as Weisberg-Lehmann test for distinguished graph structures. So this is the rather optimistic way of seeing the graph neural network. But some researchers are rather pessimistic. So what graph neural network cannot learn depth and width. So this paper says that graph neural network can compute any functions if there are enough layers and enough neurons. But if we limit the size of the layers and limit the size of the neurons, graph neural network loses power. So that is a rather pessimistic way of viewing graph networks. So it is still controversial how far we could go with graph neural network. So that's why it is a very hot topic in the field of machine learning. And another topic is explainability of graph neural network. So as you all know, the neural network is very powerful, but it is a black box. So humans cannot know why this neural network makes such a decision. So there are some trends for adding some explainabilities in the field of neural networks. So the graph neural network is also the target of the research of explainabilities. So the graph neural network explainer or some other researches are done for explaining the result of the graph neural network. So this is one example. So this heat map shows why this graph neural network make a decision of the figure. So that is one way for explaining the performance of the graph neural network. And there are so many online resources here, and still there are several problems of graph neural networks. One is shallow structures, and as I said previously, the deep graph neural network is not still not possible nowadays. So we have to think how we can make a powerful many-layer deep graph neural network. So that is a challenge. And another thing is, many of this research is for the static network. So we can, how we can adapt the graph neural network to the temporal or dynamic graph structures. That is another challenge. And a third challenge is what happens if the data has not contained the graph structure at all. So that is the general questions in the field of complex network also. So how we can extract the graph structures from raw data, that is the topic that we have to think of many times in the field of complex network also. And this is also the question in the field of graph neural network. And scalability is also a big issue, especially in the graph neural network. So the computation is very computationally demanding. So developing a large-scale graph neural network is still challenges. So our attempt is making a fast approximation of between centrality using graph neural network that appears in a CIKM this year, and this will be appeared in a conference in Lisbon next month. So the fast approximation of between centrality using graph neural network, this is done by the PhD student in our lab, and he introduced a novel graph neural network for approximating between centrality. As you know, the between centrality is very computationally expensive. So we propose a method for approximating between centrality in a fast way. So the key point is the aggregation is done separately for incoming edges and outgoing edges. And another point is those own features are not aggregated. So when we aggregate it, so some other methods also aggregate as its own features, but this method skips its own features. And this is a rather minor topic, but nodes with no shortest path are identified, and the corresponding rows in adjacency matrix and its transpose are set to 0 in order to save time for the computation. So so his slice is in a different slice. So this conference appears in a CIKM this year, November. So this schedule just overlaps this Marami conference. So I wanted to attend both the CIKM and Marami, but it is not easy to visit Beijing and Dijon at the same time in a very short time. So I gave up CIKM this year. But proceedings is available. So you can check the proceedings later. So as I said previously, the between centrality is hard to compute, because it is very time consuming. So we propose a graph neural network in order to approximate the between the centralities. And the between the centrality is, all of you know, so I will skip. And there are several approximation methods in, rather, old traditional method of approximation. So, but they're still, take much time for the large graphs and the lower ranking accuracy. So we introduce a graph neural network for approximating, between the centralities. And there are several advantages. And the graph neural network feature aggregation is done from the neighboring nodes. So the features are aggregated to its neighbors and the neighbors of neighbors, and so on. So the 3 points for this research is that the network are directed, and the incoming edges, incoming features and outgoing features are divided. That's one point for the faster computation. And these nodes has no incoming edges, so it will not, they will not appear in the shortest path. So we can ignore these nodes for the computation of the shortest path. So that is another thing for the for this research. And the third point is nodes' own features are not aggregated. So these are the 3 points for the research, and the incoming and outgoing are divided, and the architecture for the aggregation is like this, and the loss function is like this. And we introduce Kendall tau score in order to compare the ranking. So it is rather popular. And doing a experiment using a synthetic data and the real world data. So the performance based on the Kendall tau score is better, and the computational time is rather smaller compared with the rather traditional way of computing the between the centrality. So that is the research. And okay, and this is the research done by the PhD student in our lab, and she still have not make a slide for her talk, because her talk will be next month. So I will skip this one. But her talk is about the analysis of the brain waves using a graph convolutional network. And this is a research done by the Japanese student. And he tries to introduce both the local information and the global information in order to do a better performance. So these are the some of our attempts in our research regarding the graph neural network. So there are several topics to do for combining the complex network research and the deep learning researches. So one promising direction is the explainable AI. So this is a very famous phrase. XAI is studied by many researchers, and some references available online. And another topic is scene. This is for the image recognition. So scene graph is this is the input, and the output is some kind of semantic relation between the entities appeared in the figure. So the woman is behind the fence and wearing shoes, and like this. So that kind of graph structures can be used for the explanation or question and answering of the pictures. So that is another direction. And there's some attempts for analyzing a neural network as a complex network. So the deep compression is I already explained. And there are some attempts for the analyzing the dynamics of the training process from the viewpoint of complex network. So probably, we have many topics to do, as a researchers of complex network to the field of deep learning, I think. And this is the acknowledgement. And first of all, thank you very much for inviting me. And this work is supported by some of the Japanese research fund. And I would like to thank many collaborators, especially Dr. Xin Liu. He's a Chinese student. He was graduated in 2011 and got a PhD, and now working in a Japanese research institute right now. So thank you very much. And this is our lab, and the website is here. Okay, thank you very much.
We have time for questions.
Okay.
I want to know if there exists
Pre-training.
Graph neural networks for graphs in general.
Pre-training graph neural network for graphs.
For image applications, we can find like ImageNet, ResNet, and in the context of the graphs.
I see. So some kind of ready-made, already learned deep learning. So I don't know for sure. So if there are more and more research is in the field of graph neural networks, then there will be a such kind of very popular standard neural network for the analysis. But sorry, I don't know about the pre-trained graph neural network. Sorry.
Is that question?
I would like maybe your sentiment about, so it's a very popular topic currently, but do you think that, for instance, for community detection or another identified problem like link prediction, do you think that it's the only method that will always be better than traditional method? Or do you think that traditional methods are still maybe interesting for some problems? Or
So that is important point. So many machine learning researchers do the research of network embedding, and performance is better in the field of classification and link prediction. But these two are the main tasks that they are focusing on. But we know that there are several tasks in the field network. For example, finding a diameters or clustering coefficient. For that type of task, the network embedding is not so good. So we have to think, what task is good for the network embedding, and what tasks are good for the traditional approaches of complex network. So that is a very important point. And as far as I know, the classification and the link prediction is the two main tasks that network embedding is good at.
Yes. Do you really believe that network embedding is good? Because people say that it's good, but when you have a nice training, all is dependent on the training. So what is good, in fact, people say they can show you that it seems good, but they have a very nice training, so I really, you have a graph, and you know that you are reducing the dimension when you embed this graph. You cannot go back from the embedding to your graph. There's no way to go back. So you are losing information.
Yes.
So everybody is saying, yes, it's good because it's new, I would say, but is it really, how can we be be sure that it's always good. Let's say for community detection, you know that we don't know what is community detection really, because there's no real definition. So people will say it's good for community detection, but it's good. Is it good because we have a good training, or is it I take a student, I tell him to do deep learning on your network. Do you think that it will work easily, or?
Yeah. So the yeah. That is a good question. And yeah, as I said, yeah, I personally don't like the network embedding, but yeah, many machine learning researchers likes because the performance is good. But yeah, the performance is good in the assumption that the good loss function is defined, and we can design an optimizing method for that loss function. So yeah, that is the assumption for the good performance, and that assumption is not always true. So yeah, your comment is right. So the network embedding is not so simple way. So yeah, if it is carefully designed, the performance is much better than the traditional ways. But so there are several caveats. So we have to care. So So we have to design a loss function and the optimization function. So that is the point that we have to think of in order to check the performance of the network embedding. So.
And this is not very easy. Do you think that it's easy to design a good loss function?
Yeah, it is a kind of engineering and not so mathematically clear. So it is it may not be so easy, I think.
I will catch it in the case of today's functionality prediction. How do you train the network? You have a lot of graphs or only one graph at the entry of the network?
In the case of the synthetic network, many networks are generated. That's a synthetic network, and it is trained. And after that, that trained network are used for the real network because real network has not many variations. So we use the many synthetic network for training.
Do you know if there is some work to extend network embedding to temporal networks?
That is one work that I found in this one. But that appears this year, and I still have not checked in detail, but this is an attempt for the temporal network. But I know that temporal network is a very difficult topic in the field of complex networks. So I don't think it is easy to embed the temporal network. So I think there should be some many other researches for this year or next year. So that is what I can answer right now.
I have one question about the explainability of neural networks. You mentioned some more about the graph who explain neural networks, but how we can explain this with graph? We will analyze the network as a graph, but we can explain it with measurement, with shortest path, but not semantically explanation.
Defining the explanation is not easy. And many researchers define explainability in a different way. So in this research, the explanation is defined as a heat map, and some other researchers define the explainability as the path of the network. So which node contribute the center node? So that is another way of explanation. So this is also hot research, and many researchers define explainability in a different way. Yeah, yeah. So that is the
based
answer.
on graphs.
Yeah, 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 yeah. Mm.
That's, okay. There is another question. Thank you very much.
Okay. Thank you.